Okay, welcome to our last and final podcast for this unit and for the year. Yes, you can cheer because we are about done. So this is going to be about the energy involved in physical changes, but we can actually turn it to the energy involved in a chemical change, or apply it, to find the energy of a chemical change. So there's a lot in the end of the packet we're not going to get to. And I know that just makes you really sad. It does make me sad. But where I want you to look right now is on page 18. And it is going to be a calculation, but it's not a scary calculation. So the formula we're going to be using is Q equals MC delta T. So before we use this formula, why don't we go ahead and identify the variables? So this is down number 4. So Q, and sometimes we use big Q, little q, it really doesn't matter. That is the energy or heat of a physical change. We can turn Q into delta H, or we can use Q to calculate delta H. But Q we use to talk about energy or heat. That is not temperature. Temperature is a reflection of energy or heat, but they do not mean the same thing. So, and Q, when we solve for this, is going to be in joules. J. M is the mass of the substance you are heating or cooling. This will be in grams. Delta T means change in temperature. And whenever we do a change in temperature, we always do final minus initial. So what is the final initial minus the initial temperature? So we use this to heat or cool a substance, to look at the energy involved when you heat or cool a substance. So this value of specific heat, so it is an intensive property, meaning you can look it up, you can Google it. It's a consistent property for substances. And up here you can fill it in, that if something has a low specific heat, that means it doesn't take as much energy to heat or cool that substance. So therefore the substance is going to be easier or quicker. That's probably not a good English word. Sorry, it's the end of the year. To heat or to cool. Now, if something has a high specific heat, that means it's harder or it's going to be slower. That should be faster instead of quicker. Okay, just make the change. You know I don't teach English. To heat or to cool, but that doesn't mean it's not important. So the specific heat for water is 4.184, and the unit is a joule. This should be per gram degrees Celsius. Oops, not crossing it out. The unit should be joule per gram degree Celsius. Now, you have experienced specific heat. So let's imagine on a hot August day in Texas, and somebody has a pool, and you go outside, you can see the pool. So let's assume that they all have the same mass, and if you look out, they're under the same heat source. But we see a pool of water, we see a concrete decking around the pool, and we see some beautiful black wrought iron chairs. So we're assuming the same amount of mass, but I want to ask you, are they all going to be the same temperature? And I'm sure most of you know that they are not going to be the same temperature. Those black wrought iron chairs, I don't think any of you would want to sit in them because they're going to be really, really hot. They'd burn your buns. You could walk on the concrete decking, but it's still going to be pretty hot. You're going to probably walk really fast on it. But then that water is going to feel really nice. So that property is specific heat. So water has a really high specific heat, so it takes 4.184 joule to take 1 gram of water and raise it 1 degree Celsius. Compared to a metal, like the iron, has a very, very low specific heat. It's about 1/10 of the energy. So that's why metals get about 10 times hotter in the same heat. If you're ever cooking, you don't grab the handle of a cast iron pan because it's going to be really, really hot. That is specific heat. So to do these calculations, you're just going to list out the variables. Let's make this, it's the end of the year. Don't worry about a centigram. Let's just change this to a gram. So calculate the heat required to warm. So let's list out my mass is 750 grams. Look at your delta temperature, change in temperature. So final minus initial. So we raised it 70 degrees Celsius. And it's water. Water, I'll give you this, and in fact I gave it to you right above, 4.184 joule per gram degree C. So I want to assign Q. Formula I'm going to use is MC delta T. So now you just plug in 750 is your mass, plug in your specific heat, and then you plug in your change in temperature. And then now you can pick up your calculator, which I am doing right now, times 4.184 times 70, and that's the amount of energy. Now this is in a joule, and as we know, a joule is not very big itself. So 219,000, and I'm going to change my sig figs in just a minute. So that's really big. So we know that there's 1,000 joules in 1 kilojoule. So if we use that and we say 1 kilojoule, there's 1,000 joules. We're going to divide it by 1,000. That's how we can change this to 219.7. And temperature sig fig wise, we could even change this to 220 kilojoules. I would take either of those if you had the right label. So it's going to take a lot of energy, but you're trying to heat that water 70 degrees. Now you can also use this to identify an unknown substance because C is your intensive property. So we can use it to identify. So read this label or read the problem, 20.40 joules. I know if it's a joule, that unit, that gave me a Q. And I have a mass of 10 grams. And how much did we change the temperature? Well, this time you lowered it 35 to 42. So it actually went cooled 7 degrees. Well, realize we kind of skipped this, that when you heat something up, that's going to be a positive Q. It takes energy. But when you cool something down, that's going to be a negative Q. It just means that that energy was released as it's being cooled down. So actually, this is a negative Q. You can never have a negative specific heat or a negative mass. So if you ever get a negative one of those, you just know that you didn't cross out the signs. So now we're just going to plug in. I don't know the specific heat. So now solve for x. So 10 times 7 is 70. So you're going to take 20.4 divided by 70. So x is your specific heat. And again, the negative signs are going to cancel out. So 2.4 divided by 70. And it's 0.291 joule per gram degree C. And if you have a page that has all the specific heats of different substances, you look and you match that up, and that would, whatever metal that matches closest to, that would actually be the specific heat for that metal. I don't know if this is copper or not. Okay, so specific heat, if you see C, you need specific heat. If you're cooling or heating a substance, you're going to use Q equals MC delta T. Okay, so now let's turn to page 22. Now we're going to use Q equals MC delta T, and we're going to use this actually in the lab in an activity to actually calculate the Q value. So heat lost, heat gain. Heat is always transferred. When we have energy, energy is always transferred. And it always flows from high to low. So if somebody is really cold and you are warm, you hug them, you're transferring your warm heat to them. That's what happens if somebody has been out lost in the wild. They find people, they're going to actually use their own body heat to try to warm them up. So if you open your door and if your mom ever says, shut the door, you're letting the cold in. You're not really letting the cold in, you're actually letting the heat out. Energy is always transferring. We have chemical bonds break to make thermal energy. Thermal energy can make kinetic energy, which is movement. So we're always transferring our energies. So we're going to use this concept, and heat lost is a negative Q. It's going to be equal to heat gained. That's a positive Q. But the magnitude of the Q itself is going to be the same. So we're going to assume, this is a big assumption, we assume that we get 100% transfer. We know that that really doesn't happen. We're going to lose some to the environment, but we assume that we're going to get that. So we're going to use a concept that you're probably very familiar with this heat transfer. If I take something hot, let's take a hot piece of metal, let's put it into a cup of water. The metal is going to cool down, so it's going to lose the heat, but that heat is going to be used to heat up. The energy is going to be used to increase the temperature of the water. That is a transfer of heat, so the process we call is a calorimeter. So typically we use this in a coffee cup, and we call it a coffee cup calorimeter because that is coffee cups are made out of styrofoam. Styrofoams are good insulators, and again, we're trying to reduce the amount of the heat transferred to the environment. Now, what we're going to use isn't going to be as good, but we're going to use a candle, and a styrofoam cup would kind of melt if we try to use a candle. So what happens is we just have to use this calculation twice. So look at what we know. We have the mass, but it's of a metal, is 55 grams. Oops, this should be a gram. And we have the initial temperature of the metal is 90 degrees. So I'm just kind of writing down what I know. And then I have a mass, but it's of the water. It was initially at 22 degrees. And then I have a final temperature of this is metal and water. So this is both of them. They come to a equilibrium temperature. So look, just with this, what we know. I can figure out how much the metal changed, and I can figure out how much the water changed. So just subtract, again, final minus initial. So the metal went from 90 degrees to 23.4 degrees. But the water, so it cooled down. The water went, final minus initial. Sorry about that. Let's go this the right way. The metal cooled down. There we go. They have the same final temperature, minus 22 degrees. So this only heated up 1.4 degrees. That's what happens when I don't try to use my calculator. I'm getting this bad. It must be the end of the year. And then we know that 23.4 minus the 90. Again, it cooled is why it's negative. So I know temperature changes for the metal and for the water. I know the mass of the water. I know the mass of the metal. Problem is I don't know the metal because I don't know the specific heat. So this is telling me I need to find C. Well, I know C for the water because I know I'm heating up water. So let's calculate the heat gained by water. So that's going to be the mass of the water, specific heat of water. So your whole focus is now going to be just on the water. So I know that the mass of the water was 250 grams. I didn't write that down. I am sorry. So the mass of the water is 250 grams. Specific heat of the water is 4.18, and the water changed 1.4 degrees. Remember, the reason we don't see the same temperature change is because of that specific heat property, times 4.18 times 1.4. So the water gained 1,463 joules. Okay, well, where did this heat come from? It came from the metal. So now I know that this heat gained is actually equal to the heat lost, numerical wise, except that heat lost is going to be negative 1,463 joules. So the quantity is the same. The only thing that changes is the sign, because heat loss equals heat gained. And so what are we going to do next? Let's just do the same formula. 1,463 joules. Now I know the heat, I know the mass, but this is all going to be for the metal. That's the heat lost by the metal. It's going to be equal to the mass of the metal. So we're using the same formula, but now everything is about the metal. I don't know the specific heat of the metal. And I know that the temperature change of the metal was negative 66 degrees. Again, the negatives are going to cancel. So you have 1463. It's going to be divided by your mass, divided by the temperature change. And you get, for the specific heat, is 0.399 joules per gram degree C. So then we look at our chart, and what is the closest to that? And if you look right here, see how copper is the closest to that? Then we're going to say, we would say that this substance is most likely copper.